is how much sugar is in the tank initially. This is a no-brainer. Anyone could really answer this one. It says it's pure water initially, and that there's the solution that's going in hasn't gone in yet. It's starting to enter it. So, but initially at time equals 0, there is 0 kilograms of sugar in there. So it's actually already answered. And where this was pretty easy, we're actually going to use this down the road for some of our other questions. In part B, it asks us to find the amount of sugar in the tank after t minutes. So let's go ahead and label some variables here. The amount of sugar we're going to say is equal to A of sugar. And we're going to, since we're dealing with concentration as well, we're going to say CS is equal to the concentration. Had a little weird hiccup there. All right, so with this information, how to classify this problem. Even if you weren't in differential equations, you would see in any level of calculus, really, unless you hadn't gotten beyond limits yet, that this problem contains a keyword here. It contains rate, and it actually contains this keyword twice. And we know that any rate, anytime we have something dealing with a rate, we have the derivative of something. And we know if we were going to model this problem as a part of an equation, we'd have to include a rate or a derivative. And as one of the explanations in the beginning of class of what differential equations is, it's basically anything with a derivative, whether it be a first or a second or a third. So we know that this is going to be a differential equation, so we're going to begin to model it as such. We know that the derivative of A with respect to time, basically this is just saying what amount is in there with respect to time and how that changes. Well, how does this change? We know that there's a rate of solution going in, and we know that something's coming out. So we know something's going to add to it, something's going to subtract from it. So we know that the rate in, and this is actually a positive coefficient here, it's hiding initially, but the rate in, and then that's subtracted by the rate out. Okay, so now that we have some form of differential equation here, we'll begin to solve for the rate in and the rate out. We know that we'll just restate this here, dA over dt equals rate in subtracted by rate out. All right, so rate in, it's actually stated here somewhat discreetly. We know that this amount per liter, this concentration, we want that not in a concentration form, we want amount per minute. So we have 0.03, and that's kilograms per liter. And then to get that in amount per minute form, we just multiply that by the rate at which it's going in, which is 7 liters. Whoops, that looks messy. 7 liters per minute. And then we can see the units cancel here, and we get 0.21 liter, sorry about that, kilograms per minute. Now a rate out is a little more difficult to solve. Rate out. All right, so thinking about rate out, we know that the rate out is this rate. It's going out at that rate, but we don't know the concentration. We know that it's going in at a specific concentration, but the concentration in the tank is constantly changing. That rate in is adding to that concentration, so it's going to be variable to the rate in. So we'll just label that as the amount at some time t over 2,660. There's our concentration with respect to time. And then that's going to be in kilograms once again and in liters. And then by this rate here, 7 liters per minute. And then this just simplifies to A to the times 1 over 380 liters or kilograms. Why do I keep doing that? Kilograms per minute. All right, so now we can define our rate in and a rate out. We can write out the differential equation dA over dt equals 0.21 subtracted by a times 1 over 380. All right, now this is almost in standard form. We just gotta shuffle around some variables. We have dA over dt plus a over times 1 over 380 is equal to 0.21. All right, wonderful. So we have this in standard form. And now that we have it in standard form, we can actually derive a few of its attributes. We know that since this is the first derivative, we know that it's a first order differential equations. And since we know we can separate these variables, we could move this a around as we please, and we kind of already showed that. We know that it's a linear differential equation. All right, so knowing these, we can perform certain actions on this to get into a function format. But before we move on to that, I wasn't able to use the applet, but I did pull this up on Safari. Oh, not that yet. This is the direction field we're given by this differential equation. I actually have it right here. And obviously the y is going to be the amount. And we can just barely see that by this direction field, starting at the very bottom here, we can see that it's got a pretty sharp slope, and then as it goes up, the slope starts to go off, so it would travel something along those lines, something like that. But anyway, given our initial condition on this, we can actually derive our function here, but we're actually going to solve that via doing some integration. So now to rewrite this as a function, we need to perform an integral. And to do that, we got to take a couple steps. We know that our p of t, and this specific one, is equal to 1 over 380. So our mu of t would be e to the integral, and that integral performed on this actually performs nicely. It simplifies to t over 380. All right, so now we just have to multiply this term into our equation. So we have dA over dt, and this is going to be times e to the t over 380, plus, and then we're going to rewrite this so it's going to be easier to perform. We're going to have e to the t over 380 over 380, and then multiplied by a equals, and then nice enough, this is going to look just like that. All right, so now we can shuffle this around a little bit so we can perform the integral a little bit easier. We have d over dt of e to the t over 380 times a, and that equals the same integer multiplied to the e over here, t over 380. All right, now this left side, I should have given myself just a little more room probably, but this left side here is just itching to be integrated, so we're going to do that. We have the integral of this side, and then we have to do the same to the other per algebra. And this goes away nicely. We have e to the t over 380 a equals, and then to perform this integral, it's a little complicated, but not too complicated. We just have to multiply this numerator of the power to the beginning of this term. So we have 0.21 times 380, and that's going to give us 79.8 e to the t over 380. And then our constant of integration as always. And we almost have it in function format. We have a equals, since that's divided out, that's going to divide out here, 79.8. And then we have plus, and then we're just going to write this up next to it with a negative power to show that it should be in the denominator. E to the negative t over 380. And there we have it. We have our general solution. General solution. All right, now to solve for our particular solution, it's not given to you right slap in the face. You have to do a little digging. And based on this problem, we know that initially, our initial condition, there is 0 kilograms of sugar in here. So we know that at a of 0, at this time initial, there is 0 kilograms. So we're actually going to use that to solve for our particular. We know that, we'll rewrite that over here in a different color. A of 0 equals 0. And that's our initial condition. Yeah, I should have kept that I. Anyway, 0 equals 79.8 plus CE, and then this just all boils down to 0 anyway, and anything to the 0 is just 1. So we have C on the right side, and then all we have to do is subtract the, what am I doing? I wrote in a plus, I think, on accident. Whoops. Oh, no, that's right. So, yeah. So we have C is actually equal to negative 79.8. All right, so now we can plug in for our particular. So our particular solution is equal to A equals 79.8 subtracted by 79.8 e to the t negative t over 380. All right, now that's actually our answer for the first part, the second part of our problem. It asks at time t, how much, what's the amount? And we know the amount is that at time t. And so now we have to solve for this next condition it gives us. At 60 minutes, what's the amount? And not only what's the amount, but what's the concentration? So that's just going to be the amount over the total amount of capacity of the tank. So we have that A of 60 equals 79.8 subtracted by 79.8 e to the negative 60 over 380. And then there you have it. We could simplify this a little bit further, but that's not really necessary. This could be 3 over 19th. But to just keep this nice and simple, we're going to rewrite this for the concentration. The concentration of sugar at time 60 is equal to A over 2,660 is equal to 79.8 subtracted by 79.8 e to the negative 60 over 380, and then that all over 2,660. Boom. And then we're done. And then that gives us an about answer of 0.004318. All right, so there's our answer, and that's kilograms per liter. And so, just kind of show on this graph over here that yes, that did solve for our initial condition. It looks very nice. And then we go ahead and plug in our function. We can see that this term is actually transient. As you go down and down and down, it gets closer to 79.8, but it never quite reaches it, so it goes away. So I hope that you've all enjoyed this, and I hope it was very informative, and thank you very much.